Welcome to this discussion. Today's paper, Janus, Decoupling Visual Encoding for Unified Multimodal Understanding and Generation, proposes a novel architecture for multimodal models. The authors argue that existing unified models suffer from a critical limitation. What is this limitation, and how does Janus address it?
The core limitation is the use of a single visual encoder for both multimodal understanding and generation tasks. These tasks have fundamentally different requirements. Understanding needs high-level semantic information, while generation requires fine-grained spatial detail. Forcing both into a single encoder creates a conflict, leading to suboptimal performance in at least one task, typically understanding. Janus solves this by decoupling visual encoding into separate pathways, one optimized for understanding and one for generation, while maintaining a unified transformer architecture for processing. The decoupling seems intuitive, but what are the practical implications of this architectural choice? How does it impact the model's flexibility and performance?
The decoupling offers significant advantages. First, it eliminates the trade-off between understanding and generation performance inherent in single encoder models. Each pathway can now independently select the most suitable encoding method. Second, it enhances flexibility. Janus can easily incorporate additional modalities, audio, point clouds, etc., by simply adding another independent encoder pathway. Our experiments show that Janus outperforms previous unified models and even matches or exceeds the performance of task-specific models, despite having a comparable parameter count. You mentioned the use of a unified transformer architecture. Can you elaborate on the specific components and their interactions within Janus?
Janus uses a single autoregressive transformer. For text understanding, it employs the LLM's built-in tokenizer. For multimodal understanding, it uses SIGLIP for image encoding, mapping the features into the LLM's input space via an understanding adapter. For generation, it uses a VQ tokenizer, mapping the codebook embeddings to the LLM's input space via a generation adapter. These feature sequences are concatenated and fed into the LLM. A standard prediction head handles text, while a separate, randomly initialized head handles image generation.
The training procedure appears to be a multi-stage process. Can you detail the stages and their objectives?
Yes, it's a three-stage process. Stage I trains the adapters and image head, connecting visual and linguistic elements within the embedding space. The visual encoders and LLM are frozen. Only the adapters and head are trained. Stage 2 performs unified pre-training on a multimodal corpus, unfreezing the LLM and training all parameters except the encoders. We use a mix of text-only, multimodal understanding, and visual generation data. Stage 3 involves supervised fine-tuning with instruction tuning data to improve instruction following and dialogue capabilities. All parameters except the generation encoder are fine-tuned.
The paper highlights several ablation studies. What were the key findings from these studies regarding the effectiveness of the decoupled visual encoding?
The ablation studies confirm the importance of decoupling. Using a single VQ tokenizer for both tasks resulted in good generation but poor understanding. Using a stronger semantic tokenizer improved understanding but still lagged behind Janus. A model trained solely for understanding, using the same strong semantic tokenizer, significantly outperformed the unified model with the single encoder, demonstrating the trade-off inherent in the single encoder approach. This clearly shows the benefits of decoupling.
The paper mentions potential extensions to Janus. What are some of the most promising avenues for future research based on this architecture?
Several extensions are possible. For understanding, stronger vision encoders like EVA Clip or Intern VT could be used. Dynamic high-resolution techniques could handle higher-resolution images. For generation, finer-grained encoders like MoVQ Galang could improve detail preservation. Different loss functions, or a combination of autoregressive and parallel methods, could also be explored. Most importantly, the modular design makes it straightforward to add new modalities, making Janus a highly extensible platform for future multimodal research.
The results on various benchmarks are impressive. Can you summarize the key performance gains achieved by Janus compared to state-of-the-art models?
Janus consistently outperforms comparable unified models on both understanding and generation benchmarks. It achieves state-of-the-art results on several datasets, even surpassing some task-specific models with significantly more parameters. This demonstrates the effectiveness of the decoupled architecture and the potential of Janus as a powerful, general-purpose, multimodal model.
What are some of the limitations of the current Janus model, and what future work could address these limitations?
While Janus shows strong performance, there's always room for improvement. One limitation is the computational cost of training such a large model. Future work could explore more efficient training techniques or model compression methods. Another area is exploring different combinations of encoders and adapters to further optimize performance for specific tasks. Finally, more extensive evaluation on diverse and challenging datasets is needed to fully assess Janus's robustness and generalization capabilities.
The paper emphasizes the simplicity and extensibility of Janus. How does this simplicity contribute to its potential impact on the field of multimodal AI?
The simplicity is crucial. The decoupled architecture is easy to understand and implement, making it accessible to a wider research community. This extensibility allows researchers to easily adapt and extend Janus to their specific needs and datasets, fostering collaboration and accelerating progress in multimodal AI. The clear separation of concerns also makes debugging and analysis easier.
The qualitative results presented in the paper, particularly those involving meme interpretation, are quite compelling. Can you elaborate on the significance of these results?
The meme examples highlight Janus's superior fine-grained understanding capabilities compared to models using a single visual encoder. Janus accurately interprets the text and emotion in the memes, while other models struggle with text recognition or object identification. This demonstrates the practical benefits of decoupling for tasks requiring nuanced visual understanding.
The authors conclude that Janus is a strong candidate for next-generation unified multimodal models. Do you agree with this assessment, and what factors contribute to this potential?
I strongly agree. Janus combines strong performance, flexibility, and simplicity. Its modular design allows for easy extension to new modalities and tasks, making it a highly adaptable platform for future research. The decoupled architecture addresses a fundamental limitation of existing unified models, paving the way for more powerful and versatile multimodal AI systems.
What are some potential applications of Janus beyond the benchmarks presented in the paper?
Janus's capabilities extend far beyond the benchmarks. Potential applications include advanced image captioning, visual question answering, image generation for creative tasks, and even more complex tasks involving multiple modalities. Its ability to handle diverse input types opens doors to applications in robotics, medical imaging, and scientific data analysis.
Finally, what are some of the key takeaways for researchers and practitioners interested in developing and deploying multimodal AI systems?
The key takeaway is the importance of considering the specific requirements of different multimodal tasks when designing model architectures. Janus demonstrates that decoupling can significantly improve performance and flexibility. Researchers should explore modular designs that allow for independent optimization of different components, leading to more powerful and adaptable multimodal AI systems. The simplicity and extensibility of Janus make it a valuable contribution to the field.
Thank you for this insightful discussion.